It's electric.
Let's talk about electrostatic quantization and Coulombs law. Today we're looking at some of the mathematics that goes into electrostatics. First thing is some useful units and math prefixes to know when it comes to building cool things with electrostatic charges. The first is the symbol C, capital C, and that stands for Coulombs, C-O-U-L-O-M-B, named after French physicist Charles Coulomb, who we name for the unit of charge. So just like Newton's is to measure forces, Coulombs, capital C, is to measure charge. Next, we have the symbol E for the charge of an electron, which turns out to be a very, very small number. It's negative 1.6 times 10 to the negative 19th coulombs. It's such a small number, it pretty much almost means like nothing, where you have a decimal place moved over 19 places. And that actually was only measured in the last 100 years. Right here around Chicago, at the University of Chicago, Robert Millikan, for his groundbreaking work, Crazy Millikan Oil Drop Experiment. He got the Nobel Prize for measuring the charge of an electron. If you take more advanced college physics, you have to actually do the experiment. It's a crazy experiment. You pretty much go blind staring at oil drops. Next, there's the symbol N. That is the metric prefix for nano. That is for 10 to the negative ninth. That means billionths of a place. So, for example, if you're building an e-reader, like the Amazon Kindle, and eventually we'll have color ones, which will be cool, and then flexible, like almost like a real newspaper or magazine, you're talking about little tiny charges that could be on the nano coulomb scale, which is a billionth of a coulomb. We also have the metric prefixes little m, milli, and big M, mega, which is for 10 to the negative third, a thousandths, and 10 to the sixth for a million. So we could have millicoulombs, megacoulombs, and finally you could also have the Greek letter mu, which is not to be confused for coefficient of friction, but in this case for micro, which is for millionth, 10 to the negative sixth. Moving on, a couple other goofy things about electrical math. Some of the words we use can confuse us. So the first thing is to realize that a neutron is not the same thing as being electrically neutral. So if you remember, there are three main subatomic particles. Atoms are made of protons, electrons, and neutrons. Protons and neutrons are in the nucleus. They have pretty much the same mass. And then electrons are on the outside. And electrons are a lot smaller. They're like almost 2,000 times less massive, about 1,800 times actually. And so one analogy I've heard of is you can think of protons and neutrons like bowling balls, and electrons like little tiny peas. And you fling a pea around the outside of baseball stadium like Wrigley Field, and then you put a proton and neutron sized bowling balls on the pitcher's mound, and that would be like a model of an atom there. And the weird thing is that protons and electrons have the same charge, even though they're very different in size. And that's just how it is. It's kind of goofy there. Whereas neutrons have no charge. So in terms of electric charges and atoms, you can have items that are either electrically neutral or they can have a charge. They can form what are called ions. So if you're neutral, all that means is the number of electrons equals the number of protons. So for example, hydrogen has, one proton, it's got one electron. A little of your chemistry there, right? Oxygen, we got 8 protons, 8 electrons, etc. So the net charge is 0 coulombs. Now if you have an ion, if it's a positive ion, you have extra protons. So if you have a positive 2 ion, that means the net charge is 2 protons, which would be 2 times 1.6 times 10 to the negative 19th coulombs. And if you have a negative 3 ion, you would have 3 extra electrons, which would be 3 times the elementary charge of negative 1.6 times 10 to the negative 19th coulombs. So now we're ready to talk about this big idea that charge is quantized, kind of a fancy word. And all this is a fancy word for is that charge comes in little tiny packets. So the equation we can use to find the total charge of any object is Q, which represents charge, is equal to N times E. And you're probably wondering, well, why don't we use C for charge? And that's because C is for coulombs of charge. So the symbol that was picked, since we started running out of letters in the alphabet, P is for momentum, we just picked Q. There you go. Q is for charge. N is for the number of protons or electrons, and then E is the charge of a proton or electron there. So in other words, all objects, they have to contain a net charge that's a whole number of electrons or protons. And the first time the charge of electron was measured was by this gentleman here, Robert Millikan, Dr. Millikan at the University of Chicago. So a little piece of Chicago for you here. We got a deep dish pizza. We also have some Nobel Prizes at University of Chicago. So it's kind of cool. And I like to use what's called the donut analogy to help you understand this. So my little guy, my son loves to get donuts. And, every once in a while we'll let him have one. Let him live on the edge there. But what's weird is, sometimes after eating a donut, he wants to have another one. And so being a good parent can't let your kid pork out on 10 donuts all the time, right? So maybe we'll let him have another half a donut. But the point is, when you go to Dunkin' Donuts, you can't say, I would like to buy 3.5 donuts or 3.25 donuts. They'll be like, you're nuts. Go away. You have to buy either a whole donut or half a dozen or a whole dozen, or sometimes even have a baker's dozen. You get that 13th donut as a bonus there. So anyway, the point is, charge is the same way. So for example, if you had a net charge of negative 3.2 times 10 to negative 19th coulombs, that's 2 electrons. But you can't have something weird like 3 times 10 to the negative 19th. You can't have 1 3/4 of an electron. It just doesn't happen that way. So charge is always quantized, comes in discrete packets. See if you understand how quantization of charge works. So what would the net charge be of 2 electrons attached to 3 protons? Well, if you think about it, if you have negative 2 electrons and positive 3 protons, the net charge would just be positive 1 protons there, or positive 1.6 times 10 to the negative 19th coulombs. How about 4 electrons attached to a neutral atom? Well, if you have 4 electrons attached to an atom that's neutral, you would have a net charge of negative 4 electrons, which would be 4 times negative 1.6 times 10 to the negative 19th, which would be negative 4.8 times 10 to the negative 19th coulombs of charge. Next, C, what if we had charge A of negative 3 coulombs, which is in contact with charge B of positive 9 coulombs? What would the net charge be? Well, if we have 2 objects that have 2 different charges, when they're in contact with each other, the charges will redistribute, and we'll get a net charge of negative 3 plus 9 will be positive 6 coulombs, distributed between both object A and B. Next, here's another concept check question on charge quantization. Which of the following charges would be impossible? A, Q equals 3.2 times 10 to the negative 20th coulombs. B, Q equals 6.4 times 10 to the negative 19th coulombs. C, Q equals 1.12 times 10 to the negative 18th coulombs. Or D, Q equals 4.8 times 10 to the negative 19th coulombs. So let's give you a minute here, see if you can figure this out.